So it's a pleasure to be here. I've really enjoyed my visit so far today. And so I'll try to share with you some of the things I've been thinking about and worrying about. At Nvidia, we're engaged in a project aimed at building an exascale computer, one with sustained performance of 10 to the 18th operations per second by about 2021 or 2022. And we're really excited about this because we think it's going to transform science. I spend a lot of time going around and talking to the people who use this machine so I can characterize their applications. And in things like climate and weather, there's this open question right now where it's clear that we're changing the composition of the atmosphere quite drastically by adding CO2 and methane and other gases. It's not clear what the actual consequence of that is because our models right now are not accurate enough. And part of it is understanding. Part of it is understanding how clouds actually function with various energy fluxes. Part of it is resolution, is basically getting the resolution of these models down to the point where they basically agree with various data that's taken and you can get reproducible results. And moving to an exascale will let us resolve down to kilometer scale grid that will give us the ability to do that. People are trying to build more efficient engines. It turns out that these models need grid sizes to get reasonable combustion chambers modeled at a level where you get reasonable modeling of the turbulent flow, even with macroscale models of turbulence. They typically have hundreds of species of chemical reagents that are reacting. Many reactions that determine the rates at which these species change from one to the other. And again, an exascale will give us the ability to simulate efficient engines in a way that we can't do today. Today we're using big approximations that often get the answer wrong compared to experiment. And in biology, people are building coupled models where they can simulate whole organs and in some cases whole organisms, down to the cell level and even the little molecular machines within the cell. In astrophysics, people are basically looking at what happens within stars when they collapse, when they're formed, and answering some of the fundamental answers, testing theories about the nature and creation of the universe. So people often ask me, well, why are computers important, to science? And the way I like to think about it is back in the 18th or 19th or maybe even the 20th century, when you're doing science, you built a large instrument. You built a telescope or perhaps a particle accelerator. Today, if you're really interested in doing science, you build a really big computer because much of the scientific discovery today is done on computer. Now, it has to be fit to models and matched to experiment, but computing has really become the third pillar along with theory and experiment that much of modern science rests on. So computers really are high-performance instruments, and I think whoever has the best instruments winds up doing the best science, and that's why we really need to build these machines. This is currently the number 2 machine on the top 500 list. The Titan machine, which is built from Nvidia GPUs, it's at Oak Ridge National Laboratories. 18,688 of our Tesla GPUs provides almost all of the 27 petaflops of performance in this. There are a comparable number of AMD CPUs that provides on the order of maybe 1 petaflops of performance, but dissipates almost half the power in the machine. The machine is 17.59 petaflops sustained performance on LinPack. That's good for the number 2 spot, but the thing to point out is that Kepler-based machines based on the K20 hold all 10 positions on the green 500 list. The machine which is number 1 on the top 500 list now, the Tianhe 2 machine based on the Intel Phi processor at the National University of Defense Technology in Changsha, China, this is about half as energy efficient as machines based on Kepler. So it isn't, doesn't even make a dent in the top part of the green 500 list. This particular machine, the one Titan, is around 2.5 gigaflops per watt. The top machine on the list is the Sabame machine at Tokyo Institute of Technology, and that machine is about 4 gigaflops per watt. The Intel Phi machines come in at like 1.2, 1.3. So a lot of people say, okay, that's great for science. What about business analytics? The big thing today is big data. Don't you need to build a different machine for that? And the answer is no. It turns out that whether you're basically trying to study the nature of the universe or simulate climate, or whether you're trying to study the nature of your business and study large amounts of data and pull actionable information out of it, the problems are largely the same, and the type of machines you need to build are the same at their core, but may differ a little bit in how you balance communications, memory, and arithmetic. But it's the same core competencies that you need. Now, building these machines and getting to the point where we can scale them is becoming a lot harder due to 3 trends. So I'm going to share these 3 trends with you, and along the way sort of share some of what I think are the solutions for dealing with the changing world. I mean, it used to be back in the good old days, it was easy to be a computer architect because the process technology got better so fast that you could kind of sort of spend most of your time out on the beach or something like that and redesign kind of the machine you used to design get a couple X speed up in performance, and everybody thought you were a big hero. And this was due to something called Dennard scaling, which ended almost a decade ago. And so let me sort of walk through the arguments about the ending of Dennard scaling and what it means. So every once in a while I tell people I'm in the computer hardware business, and they say, well, that's all about Moore's Law, right? Moore's Law doubles hardware performance every couple years or every year. And I say, well, no, that's not what Moore's Law is. And this is actually a common misconception about Moore's Law. So the answer to that question is wrong. So what is Moore's Law? So this is sort of the relevant figure from Moore's original 1965 paper, which came to be coined as Moore's Law. And you'll see that there's no computer performance on either axis here. The y-axis is number of components, meaning number of transistors on a chip, and the x-axis is calendar year. He drew a couple points, extrapolated a line through them on a semi-log plot, and predicted that number of transistors would increase exponentially, which was kind of quite a radical thought at the time. And Moore's Law is actually still quite alive and well. You can see sort of a sequence of chips here that, moving forward, we're currently, that's actually a Nvidia Kepler GPU in the upper right. We're currently building chips with roughly 7 billion transistors on them. And this is increasing exponentially over time. There's no slowdown in Moore's Law. What Moore's Law gives us is more transistors. But to use those transistors, we need to be able to power them all with the same amount of aggregate power we used for the last chip. Going from the Fermi chip in 2010 with 3 billion transistors to Kepler in 2012 with 7 billion, we didn't increase the total die power. Both of those are 150-watt chips that go into a 230-watt GPU, and that 230 watts includes the voltage regulator and the memory. So we need to power more than twice as many transistors with the same power. It means half the amount of power per transistor. Now, the way we used to get around this was what was called classic constant field or Dennard scaling, after a paper that Dennard, who was at IBM at the time, wrote in the 70s about semiconductor scaling. And what would happen is you would basically have 2 times as many transistors. So in some sense, that's giving you twice as much capability. You could then run them faster. This is basically one scaling, which basically cut the linear dimension by a square root of 2. So the width is now 0.7 in x and y, so you can get twice as many in a given area. They go 1.4 times faster because the electrons have have 0.7 the distance to go across the device. But notice my power is now up at sort of 2.8 times the capability, but my power is 2.8x. But the good news is the capacitance drops by 0.7 because the devices are scaled 0.7 in all 3 dimensions. And I can drop my voltage. And a drop of 0.7 in voltage gives me a 0.5 in power. So I basically get 2.8 times the goodness, the capability of number of transistors times their speed, at exactly the same power. And this scaling that gives me more capability at the same power is really what made possible the sort of enormous advances in serial processor performance in the 80s and 90s. It was not Moore's Law, which simply gave us more transistors. It was Moore's Law in combination with Dennard scaling, which made those transistors useful because it allowed you to power them. Well, an interesting thing happened. This is another semi-log plot due to Gordon Moore. This is from a keynote that Gordon gave at the International Solid-State Circuits Conference in 2003. And it shows the convergence of active power of chips, which is basically the CV squared F power due to charging and discharging the capacitors, the power you dissipate when you move a signal from a 1 to a 0 or back again. And the leakage power, which is basically the power dissipated by the chip when it's not doing anything, just by having the transistors, which are nominally off, not really being off. They're still a little bit on and current leaks through them. And what it showed is that the leakage power was increasing at a much more rapid rate and was about to cross over. This is because the leakage power goes exponentially with threshold voltage. As you have a smaller threshold voltage, the leakage power goes exponentially up. And what that did is it meant that to avoid making this leakage power get too large, we could no longer afford to increase or to decrease the supply voltages as we scaled to a smaller dimension, keeping the field across the device constant. Instead, we had to hold the supply voltage constant so we could hold the threshold voltage constant and keep circuits that depend on the supply voltage being a certain multiple of the threshold voltage able to work properly. So the scaling now, we can also no longer run the transistors faster because we're scaling them in such a way that doesn't permit that. So now we simply get 2 times as many transistors. That's still a factor of 2 in goodness. But now we only win from capacitance. We don't win from the supply voltage scaling. So we could get twice as much capability, but at 1.4 times the power. That's not very good. So we have sort of a choice here. We used to be at this point where we got 2.8 times the capability at the same power. Now we can either get twice the capability but burn 1.4x the power, but for something like a GPU, we can't go over 150 watts. The form factor that goes into the ability to cool the part won't admit us going up to 1.4 times that, which would be, a 220, 230 watt chip and wind up being a 300 watt module. So instead what we wind up doing is going back to the same power and getting about a 40% bump in performance. And unfortunately, things aren't even that good because due to a bunch of restrictions in the geometry rules and difficulty with scaling, the real scaling looks more like this, where we wind up getting perhaps a 20 or 30% bump in performance from a new process generation node. This is a huge difference in the way of doing business. It used to be we'd get a new process generation node, and we would make things 2.8 times better from process. Now we get a new process generation node, and they get 20% better. That's a lot less than 2.8x. I loved a summary of this that Bob Colwell, who's the director of the Microsystem Technology Office at DARPA, gave last summer at the Design Automation Conference, and this where he was giving a talk on a similar topic. And this is the quote from him, which is, Moore's Law gives us more transistors. Dennard scaling made them useful. Notice the past tense there. So this is now combined with another trend that's going on, which is sort of the end of ILP. So during the 80s and 90s, we got more transistors, and Dennard scaling made them useful, so we could basically run all these extra transistors at the same power that we had before and turn the clock rates up each generation. What made it possible to turn them into serial performance, and by the way, I apologize for the axis on this. This is performance in picoseconds per instruction, so lower is better. Had I had this chart to do over again, I would flip it over and do the reciprocal, which is instructions per picoseconds. More people are comfortable with goodness going upward. But this is the original chart out of an ISAT study I led in 2001. And what we observed is the reason we were able to get this 52% per year, which is sort of what people got out of computer performance in the 80s and 90s, is we had technology to turn more transistors into single-thread performance. And it really came from two things. It came from deeper pipelining, basically making each pipeline stage take a smaller number of gate delays, and doing more things wide, basically issuing more than one instruction at a time. And to give you the two extremes, in 1980, the best microprocessor you could buy was an Intel 8086, the original x86 architecture. It had a pipeline stage that was approximately 100 fan out of 4 inverter delays, which is a way of commonly measuring delay in a technology-independent unit. So 100 gate delays per pipe stage. By the end of the 90s, Intel was working on their starburst architecture, the P4, which had a pipe stage that was 9 gate delays, 9 fan out of 4 inverter delays per cycle, and they double cycled the arithmetic pipeline, so they were 4.5. That was beyond the point of diminishing returns. Most people have since returned to somewhere between about 16 and 24 gate delays per pipe stage. But it's mined out. You can't get any more performance of a single thread by making the pipeline stages smaller because it's been done. That vein of ore is completely tapped. The other thing that happened here is people went from doing one instruction every 10 cycles, that was the issue rate of an 8086 going flat out, to issuing 4 instructions per cycle by the end of the 90s. In fact, there were a couple machines that people had on the drawing board at the end of the 90s. The last alpha that never saw the light of day did 8. And then people backed off, and most machines today do 4. That, again, is not getting any wider. So the instruction level parallelism that really turned transistors that we were able to power because of Dennard scaling into more serial performance is gone, right? We've tapped out deeper pipelines. We've tapped out wider issue. Machines have stabilized on both of those dimensions, and they're not getting any faster. This leads to the end of historic scaling. This is a chart due to the late Chuck Moore, a different Moore, who was at the time CTO of AMD. And he basically took a bunch of data that several of my colleagues from Stanford, led by Mark Horowitz, collected historically about microprocessor performance and plotted these various lines. This is being filmed. We do this with the mouse. What you see is Moore's Law is alive and well. That's the top line. Still going up. Lots of transistors each year. But single-thread performance has flattened out because of this combination of tapping out ILP and end of Dennard scaling. Dennard scaling really ended around 2005. That's when supply voltage stopped going down. We've peaked out on the power we can get per die, and even by AMD's accounts, the number of cores per die. We tend to differ with that, and the frequency has stopped going up. So what do you do about this? Processors really aren't getting any faster, just wider. What I mean by that is more cores. So future performance, I don't mean wider issue. They've sort of stopped it at 4 wide issue, sort of 20 fan out of 4 inverter delays per pipe stage. And actually for optimum energy efficiency, they want to be narrower and slower than that. But you get more processors on a chip. It's also the case that everything is energy limited today. Because of that end of Dennard scaling, we can't fully power all the transistors we can put on a chip. This doesn't mean that we're going to wind up with what some people call dark silicon, where we leave parts of the chip unpowered. That's actually an uneconomical way of dealing with that. What it does mean is we're going to have dim silicon. We're simply going to lower the supply voltage of these chips and run them at lower than peak performance most of the time to stay within their power envelopes. That's actually a more efficient way of dealing with it. As a circuit designer and architect, though, I actually like the last bullet here. We're now getting about 1.2x out of a process generation rather than 2.8x. It really means that process doesn't matter that much. You can be a process node. It used to be if you were a process node behind, you were dead. Your competitor's product was 2.8x better. It's hard to sell a product when you're disadvantaged by 2.8x. Now if you're a node behind, if you're clever, you can make that 20% up on better architecture and better circuits. Now to understand in this environment where things are energy limited, what really matters, here is kind of the way I view designing processors, in that a CMOS chip, and this is sort of these are 28 nanometer numbers. We're now designing 16 nanometer chips. I need to update this slide. But back in the 28 nanometer generation, we'd have a chip. It would be 20. Some of our big GPUs are close to 25 millimeters on a side. And to plop down a double precision floating point unit, that is not to scale. A double precision floating point unit is about 1/10 of a square millimeter in area. That makes it look like it's almost a millimeter on a side. That's easily a factor of 10 larger. But if I drew it at actual size, it's A, hard to draw, and B, you wouldn't see it. But the important thing is that doing a double precision arithmetic operation in 28 took about 20 picojoules. In contrast, feeding that operation, which requires moving 4 doubles, because I need to have 3 input operands, I have an output operand, and I actually have to feed an instruction in there as well, so it's a little bit more than 4 doubles that have to move around. If I move them even 1 millimeter, which is shown as the line here, it takes more energy to move 4 64-bit words 1 millimeter than it does to do a double precision floating point operation on them. The arithmetic isn't the problem. Arithmetic's almost free. By the way, the bits at the other end of that 1 millimeter wire didn't just hallucinate themselves out of space. They had to be read from a memory, right? So reading and writing those bits from memory took 50 picojoules. So if I were simply to read a relatively small memory, much as we use for our register files, move the bits a millimeter, I'm now consuming more than 3 times the energy of doing the arithmetic operation, almost 4 times. If instead I have to go 10 millimeters, I'm up to more than 10x the energy. If I had to move something from one corner of the chip to another, it's 40x, and it's even more than that. It's 100x or more if I have to go off chip and access external DRAM. So what you quickly see is that in the absence of overhead, if a large fraction of your processor energy was in the arithmetic, it would be completely swamped by data movement, and all of your energy, and hence all of your performance, since performance is limited by energy, is determined by the communication in the memory system of your processor, not by the processor core itself. Now, overhead plays a big factor, and it really has to do with how you're optimizing your processor. So to give you a comparison, in roughly comparable technology nodes, the Intel 32 is very comparable to the TSMC 28. Intel's best CPU was about 1.7 picojoules per flop. And most of the flops there, by the way, were coming out of the SIMT unit. If you factored that out, it was actually way worse than that. But I'm even going to spot them that advantage. Whereas the Kepler GPU, the one that we have in Titan, is 140 picojoules per flop. More than an order of magnitude more efficient, and actually it's more like a factor of 40 more efficient when you factor the SIMT units out of the CPU. Now, you can do even better if you build fixed function logic. If you were to take some of these operations and you were simply to hardwire a core for doing those operations, you can wind up getting them down to about 10 picojoules per op. And you may wonder how you can do that when the individual arithmetic operations are around 20. But that's 20 for a double precision arithmetic operation. When you build fixed function logic, you usually specialize data widths and convert things to integers where appropriate. And the number we tend to come up with when we look at our fixed function units, we build fixed function units for our texture filters and our rasterizers and our compositors, is about 10 picojoules per op. So it's yet another order of magnitude better. So this gap here, by the way, to me is opportunity. It means by being a clever architect, I should be able to make it so that most of my energy is dissipated in the arithmetic. I should approach that fixed function number. I'll never get all the way there because programmability costs something, but I can do a lot better than 10x. Now, one way of studying how to close the gap is to look at where the energy goes. In both a complex out-of-order CPU, like the Intel chip I showed you, that's on the right, and in an in-order embedded core. This is actually from a embedded Spark core that came out of a paper we wrote back in 2008. And what you see is that actually doing the useful work is a small piece here, AOU 6%, even in the in-order embedded. It's 4% in the out-of-order, even though it's an order of magnitude less efficient. That's because a lot of these AOU operations later get thrown away. But where does all the energy? It goes to supplying data, supplying instructions, reading the register file, which is really more of the data supply, and clocking control logic. Right? So that's overhead. What we really need to do is to drive that overhead down so that our payload, which is this little slice here, the 6%, is a much larger fraction of the overall pie. That's how we can build more energy efficient computers. Now, it's interesting. When I started at Nvidia in 2009, I was asked to give a talk at a meeting where we sort of brought all our leaders together and tried to align them on strategy. And I was trying to push people to do energy efficient design because I've been reviewing a lot of projects and have been appalled. Actually, just that people couldn't answer my question, which is, oh, you're cycling that memory over here. What does that cost? I go, what do you mean, what does that cost? I go, well, how many picojoules is that? And I haven't got a clue. And my analogy was, if you went to the grocery store and you just started throwing things into your cart and you didn't know what they cost, when you got to the checkout counter, you would have a very rude surprise, and depending on how you had in your pocket, you may be taking your cart back and putting a bunch of things back. Well, we had the same kind of rude surprise when we would build chips without knowing, how much energy each thing was, and we'd get to the checkout counter, which is when you tape the chip out and you get it back from fab and you power it up and it overloads your power supply. So I came up with what they started calling my shopping list, which isn't quite accurate because it's not really your shopping list, but it's more the price list of what different things cost. And we now have a wiki page that lists all of these things called Bill's Shopping List. They have for, here I have some sort of for 40 nanometer technology and 10 nanometer technology, what things cost. So a double FMA costs 50 picojoules in 40. I apologize for mixing technologies. I pulled data from a bunch of sources. Our projection is that in 10 nanometer, it'll be about 7.6 picojoules. So that's actually pretty good scaling. It's better than linear scaling from down this factor of 4 down here. Similarly, reading an SRAM will go from 14 to 2, about a factor of 7 improvement. What doesn't improve so much is moving the data. So already, as I pointed out in my previous slide, moving the data is way more energy than doing the arithmetic operations. That's a problem that's only getting worse as technology scales. And the reason is that the energy of doing logical units is still improving by basically that 0.7 in capacitance you get going in each technology generation. But the problem is a long wire is still a long wire, and it's still 200 femtofarads per millimeter, even as you scale, because it remains, the length of that wire doesn't scale with the length of the logic gates. If you have to cross the chip, you still have to cross a 20 millimeter chip. And so you only really gain by sort of circuit efficiency there. Similarly, the memory technology is improving. DRAM pin bandwidth is expected to go up. Better DRAM interfaces, for the most part, are driving the access energy of the DRAM down from around 30 picojoule per bit today to in the 2 to 5 picojoule per bit in the future. And our goal to get to an exascale, by the way, the goal for the exascale machine is to do an exascale in a 20 megawatt power budget. And to do that, we really need to get down to about 20 picojoules per op total energy. 4 of that in this time frame using sort of a 10 nanometer technology is going to come from doing the op. A DFMA is 2 ops. That's both a multiply and an add. So we need to basically do the rest of the system in 16 picojoules, which is a pretty tough order. So here's some of the things we're looking at to close that energy efficiency gap. One of them is communication energy. So today, the way we move a bit across a chip is by using the power supply to signal a 1 and ground to signal a 0. It's almost the most inefficient way you could think of doing things. You have an enormous amount of energy. If you look at the fundamental noise sources you have to come over to get a reasonable signal-to-noise ratio, you don't need anywhere near that much energy to signal a bit. The problem is as you build transmitters that use less and less energy to signal the bit, you end up needing to build receivers that use more and more energy to amplify it. But there's a happy medium there. And this chart is actually a chart out of a Stanford PhD thesis comparing a number of different signaling technologies. Conventional signaling is the black line at the top here. It's called full swing interconnect. Roughly 200 femtojoule per bit millimeter, and limited to on the order of sort of gigahertz signaling rates, unless you want to put the repeaters very, very closely spaced. It's limited bandwidth, and on-chip wires are very resistive. People have published things down into the 20 femtojoule per bit millimeter range. This thesis was this one, so it was basically comparable energy but much higher bandwidths. We're currently working on a signaling technology that is about half of that. It's around 10 femtojoule per bit millimeter, and it's off this chart by a factor of 10 to the right. It's 20 gigabits per second. So there's tremendous opportunities to do better in the fundamental technology, moving a bit from one place to another. And since that's what's dominating power today, once you get the overhead out of the way, and is going to be even more dominant in the future, is a huge advantage. So that's part of closing that energy gap. The other one is understanding what you want to optimize with your cores. Too many people today are focused on providing single-thread performance. Part of this is a community that's, generals fight yesterday's wars. Computer architects run yesterday's benchmarks. And we have a community that's running things like the spec benchmark, which reflects single-thread performance and to some extent is completely irrelevant in an era where everything is becoming parallel. But if you want to run the spec benchmark well, you need to build machines that are out of order. They speculate. What does speculate mean? Well, it means, I'm guessing that this branch is going to go this way. I'm going to do a whole lot of work based on that guess, and if I'm wrong, I'm going to throw it all away. Right? That's not very energy efficient. If I'm willing to sacrifice a certain amount of performance, I can get much more efficiency. So this is a chart that came out of one of Mark Horowitz's students' thesis that basically shows a Pareto-optimal frontier and what technology puts you on that frontier. So basically, if you're trying to trade off energy per instruction, that's energy efficiency, against performance, only for the very highest parts of this do you want a very complex out-of-order core, 4-issue out-of-order core. As soon as you drop to a certain level of performance, I seem to have lost my mouse. There it is. You're actually that leaves the Pareto-optimal frontier, and you're better off with a 2-issue out-of-order core, and even down at relatively high levels of performance, in-order starts to dominate to provide the lowest energy at a given performance level. And today we tend to optimize our cores far too far up. So to show you again this chart, the reason why this guy is an order of magnitude more energy than the GPU is because it's optimized for that point way up to the right. And for most people, that's not what delivers value. For most people, what delivers value is something that gives you much more energy per op optimized rather than single-thread performance optimized. So we tend to refer to these CPUs as latency-optimized cores. They've got lots of things in them that dissipate energy, things like branch predictors. You want to predict a branch. You have to cycle 2 very large tables, one that says whether it's branching or not and one that says where to go. And you do that actually on every instruction because you have to do this before you know it's a branch or not. You rename registers. That's basically another table where you read your logical name of your register and you translate it to the physical register that logical name happens to be living at now. You schedule your instructions, run them all out of order, and then at the very end you put them all back into order so if anything happens, somebody looks, it looks like it all happened serially. It's all a very clever way of doing things in parallel but hiding it, sort of covert parallelism. But all of this covert parallelism costs a lot of energy. The way we build GPUs, on the other hand, which we call throughput-optimized cores, is we have a lot of threads. Well, why do we have a lot of threads? Well, the reason you're doing all these silly things over on this out-of-order core is one very simple fact, is that you can't predict whether something is going to hit or miss in the cache. And if you hit in the cache, you get your data back in maybe 3 clock cycles. And if you miss in the cache, it could take 20 or 40 or 100 or more, depending on how far out the memory hierarchy you have to do to fetch the data. So since you have this unpredictable latency, you wind up having to reorder your instructions so that the instructions that are waiting on the data back from memory get pushed to the side, and you run instructions that are logically after them in the program but are ready to run while you're waiting for that data to come back from memory. And when the data finally comes back, then you run all those instructions you left on the siding waiting for their data. That's hugely expensive to do. If you have parallelism, it's much more efficient so when an instruction accesses memory and misses in the cache. You say, okay, you're going to be a while. Why don't you move to the side? And I'm just going to run another thread. I don't have to predict which way branches are going to go to look way ahead to find instructions to do. I don't have to speculate on various things and then reorder instructions later. I can simply take work I know I need to do from another thread and execute it until the piece of data from memory comes back in the first one. So we have a bunch of threads. We grab a thread that is ready to go. That's the select operation. We fetch its instruction, we read its data operands, and we do it. Very simple, very little overhead. There's still things that we can pare down out of there, though. So this is an order of magnitude difference, actually probably more like a factor of 50 difference in efficiency. How do we pare even more out of that? So this is sort of a view of one of our GPUs. It turns out 15% of the energy in our streaming multiprocessor, which is what we call this basic unit, is reading the register file, which is actually a bunch of big RAM arrays. And so what we do is we spend a lot of time studying the codes that our customers actually run, and we discover that this is how often data is used. Most data is used exactly one time. You basically write something to the register file, you read it back out, it never gets touched again. And it gets used very quickly. The lifetime is typically under 3 cycles. So you're basically going to write it to the register file, and within the next 3 cycles, read it back out. What that means is that rather than having a really big register file needed to hold the entire state of your thread, yeah, question?
Yeah. So my question comes up there. Is that I know how in traditional sequential code, then you have a very short, typically, write to use time. Mm-hmm. But now you're multi-threading. So you said that you're going to.
This is within one thread. Yes. This is within each thread. The use time.
Okay, so a cycle means.
A cycle means with the number of instructions later in this thread.
In that thread. Okay,
yeah.
Yeah. Okay, that makes sense.
Thanks for the clarification. Yeah. So what we're doing here is we're basically saying, what if we cache the most recent reads and writes in a small register file sitting right in front of the AOU? It turns out we can access this with about 1/10 of the energy as reading the big register file, which is further away. Remember, everything is about moving bits. If we have a small thing, we can put it closer. We have to move the bits less far. Well, the results here, and this is a paper we published a couple years ago, is it saves half the energy of this 15%. So that's 7 or 8% of the energy. And what the 4 bars are is basically whether we have 2 levels of hierarchy or 3 levels, and whether we do it in hardware or software. And you see here that the software implementation of this is much more energy efficient. And the reason for that is the compiler is really good at saying, we could reuse this data right away, but only if we move this instruction here. So the compiler has more ability to sort of fix the instruction sequence to maximize the reuse and to put the data in the small register file and then trying to discover it on the fly. So the optimum here that we sort of settled on was 3 entries per thread in this small register file. Another thing we're doing to save energy is turning a traditional GPU on its side. So traditionally, a GPU executed things 32 threads at a time, what we call a warp, in parallel. And the problem with that is if we have a bunch of code and it branches, we wind up doing some of these instructions and not doing others. Temporal SIMT, which I show on the right here, is we take the same warp and we turn it on its side and we run it in time rather than in space. Now, to use the space, we run 32 different warps at the same time on the different AOUs. Now, what is the advantage of this? Suppose I branch so that only the green threads of these 32 are active. If I'm basically running 32 wide, I get 41% efficiency. Only 41% of my threads are doing useful work. The others are idling because they're on the wrong path of a branch. If I do temporal SIMT 4 wide, and I simply discard all 4 wide subunits, so I think it's subwarps, that are all off, I wind up with 65% efficiency. If I go all the way down to 1 wide, it's 100% efficient. I simply don't do the threads that are going the other way. Now, another thing this enables us to do is to realize that when we look at our code on the average GPU code, 30% of the instructions in a warp are doing exactly the same thing. I should say across all threads of the warp. So if you look at it, you do a bunch of things where you're doing different things, and then when I say the same thing, I don't mean the same instruction. They're all doing the same instruction. I mean the same instruction on the same data producing the same result. What they're actually doing is they're doing a scalar instruction that somebody turned into a parallel instruction just because that was the easy way to code it on a GPU. So what we're doing is we're turning those scalar instructions back into scalar instructions with a compiler technique called scalarization. And by turning our warps in the temporal dimension, we'll wind up with, for example, a warp running its thread 0, thread 1, thread 2, thread 3, the multiple threads of a warp doing parallel work. And then if all 4 threads of that warp, this is a small warp, are doing the same thing on the next instruction, we just do it once and share the result with all the threads. This actually winds up being about another 30% improvement because the number of operations executed drops by 29% when you scalarize a typical GPU code. Okay, so that was sort of trend 1, which was end of Dennard scaling. We get a new process node. We're only getting 20% more benefit. What do you do about it? Our customers are still demanding this kind of 50% improvement in performance each generation. What it means is that it really is the time for circuit design, doing things like more efficient signaling over wires, better memory designs, looking at the fundamental building blocks of computers and building more efficient versions of them makes a huge difference because you're not getting that from process. You need to get it somewhere else. And then also where we still have this more than order of magnitude gap between fixed function logic and even a very efficient in-order throughput optimized core like a GPU, there's still a lot of creativity, I think, that we'll never get it to close completely. But I often fantasize we ought to be able to get within a factor of 2 of fixed function logic with a very programmable engine. And to me, those are the 2 big challenges that are posed by the end of Dennard scaling. So let me talk about the next challenge that's sort of a resulting, almost a corollary of Dennard scaling, which is because we're not scaling the speed and the voltage of these transistors anymore, we aren't getting faster processors in terms of single-thread performance. They're just getting wider. We get more processors on a chip. We get more threads. And this is basically true from cell phones to supercomputers. Today, I guess this is a slide that needs to be updated. Last year, you would have a typical cell phone, say one based on our Tegra 4 part, where you would have order of 4 threads on the 4 ARM CPUs and 1,000 threads on the Kepler GPU that's on the Tegra chip. And we're projecting that that's going to basically increase by a factor of 4 between now and 2020. And simply on the supercomputer, you have order of 100 million threads today. That's going to be 1 billion, or actually some of our projections are saying more like 10 billion threads in 2020. And I find that when I talk to the average programmer, they're completely unprepared to write the parallel code needed to exploit the machines that are going to be our mainstream machines. This is not just, although I tend to focus a lot on the supercomputers because they're a nice thing to stress you to do absolutely the best you can in terms of energy efficiency and to deal with the extreme levels of parallelism now. I'm talking about programming your iPhone in 2020 is going to be a mostly parallel task, right? And yet we tend to teach most of our students serial programming. We teach them theory of algorithm with big O notation. Nobody cares about the number of operations. Those are cheap. The only sort of algorithm theorist I know that's really working on communication is Jim Demel at Berkeley, who has a lot of work he's doing on communication avoiding algorithms. We really need to focus on what the machines are going to look like out in the future and prepare students to program those. Now, parallel programming is inherently a very simple activity. So here's an example of what's a very simple code. Say I want to do molecular dynamics code. Well, it means for every molecule, so that's the first thing here, I'm going to say for every molecule in this set, and I'm going to say for every neighbor of that molecule, and then for every force in some set of forces, maybe I want to do an electrostatic force and a van der Waals and Lennart-Jones, and I'll have codes for each of those. I want to compute those, and then I want to say, do a reduced sum of all of those forces for for a particular molecule and all of its neighbors, and reduce that into that molecule's force variable, so I know what force is acting on the molecule. Then there'll be a little code that I didn't show you that after this is all done, pushes all the molecules. And it's inherently simple. Why is it simple? Because I haven't tried to make any mapping decisions here. This is completely machine-independent code. It turns out that if I were to do this for a GPU, I would take some number of these basic tasks of computing a force and group them into a thread, and then group those threads into warps, and group those warps into CTAs, and dispatch that. But I'm making a lot of decisions there that I would make differently if I had a different target. If I was targeting it for a multi-core CPU, I would put many more tasks into a thread because they're heavier weight, and factor it differently. I would also stage the data up and down the memory hierarchy differently, even within one of those 2 genres, depending on the sizes of the caches at the different level of the memory hierarchy. And if you look at a highly tuned code today, it has all sorts of machine-specific optimizations buried in the source code, because that's how people write codes. They sit down and they actually get something functionally correct in a couple of days, and then they spend a month getting performance out of it, making optimizations that are specific to one particular target machine. And then when you issue your next generation of hardware, they whine at you because their code runs slower than it used to do, because all of those specific optimizations don't apply to this generation of hardware. Well, there's something really wrong here. So here there's no machine details. All the parallelism is expressed. One of the problems when you pre-crunch things down into threads is you're limiting the amount of parallelism there. So if somebody gives you a machine with more threads or more cores in the next generation, you can't take advantage of that. You already flattened it out. And then synchronization is where programmers tend to shoot themselves in the foot or into other more vital parts of their anatomy. And all the synchronization here is inherent in the operation, particularly in the reduction. You have to wait until the forces are done being calculated before you reduce them. It's implied. I'm not I'm not allowing you to screw up and shoot yourself in the foot. Now, I do have friends who like to prove to their colleagues how clever they are by writing really complicated code. In fact, the C community has this obfuscated C code contest they have every year. And actually, a lot of parallel code would qualify for this. And so you can do things like, fork threads explicitly and acquire locks. It turns out that some large fraction of locks acquired wind up being the wrong lock. Or you're accessing a piece of data in the critical section that needs to be locked, but you locked the wrong lock for that piece of data. Jim Laris, who used to be at Microsoft Research, once wrote a tool that would analyze parallel codes and look for synchronization errors. And every piece of code they ran it on at Microsoft, it found errors. Even the code, in the core of their operating system written by their best programmers. This is just inherently hard to do. Human beings should not be doing this sort of stuff. So, I realized the answer to this. I used to be a youth soccer coach back when my daughters were of that age. And I found that as a coach, the most common advice I would be giving to my players is, don't steal the ball from her, she's on your team. And this is really kind of the lack of teamwork is what's going on here. I view sort of a parallel computation as being a team sport with three players, or at least three types of players. We have programmers whose role on the team is to come up with the algorithm and express all of the available parallelism in a very abstract notion of locality. We have tools which are responsible for taking that sort of abstract program where all of the parallelism is exposed. You have way more tasks than you have processors or threads, and assigning tasks to threads to processors, laying out the data in memory, staging the data up and down the memory hierarchy, and selecting what mechanisms to use for communication and synchronization. And then the architecture, which wants to get out of the way. As an architect, I realize that most of what the role of an architect is to do is to give the raw materials to the programming system and not to enforce any predefined notion about how those materials should be used. So the raw materials are arithmetic if you're doing calculations, and storage and communication. And so what we want to do is expose the storage hierarchy. Don't make any explicit assumptions about I want caches here or scratch pads there. We have a notion of malleable memory where we give you a bunch of SRAM arrays and you can configure them in the way that's appropriate for your application. We want to basically let you get at the communication and synchronization mechanisms with the minimum of overhead and have most of the energy going into arithmetic. So our view of what a future flow for a programmer is looks more like this, where everybody playing their positions, you have a target-independent source code, much like the molecular dynamics code I wrote you, but a little bit more complicated. I swept a little bit of stuff under the rug there in the interest of keeping the slide simple. We have a bunch of mapping tools which will take that target-independent source and create a correct executable. Hopefully one that's actually reasonably close to good performance. But it's not going to be possible to automatically get everything right, at least not the first time. So then you'll have a bunch of performance analysis and visualization tools that will look at executions of your target-dependent executable and basically give you feedback so that either via automatic or manual means you can take that feedback and give mapping directives that will basically assist the mapping tools in doing a better job of making their machine-dependent decisions. Notice that nowhere am I putting the machine-dependent decisions in the source code, because then this source code would become non-portable. I wouldn't be able to take it to a different class of machine or even another machine of the same class next generation. So I want to factor out these machine-dependent decisions, make as many of them as I can via tools automatically so I'm not burdening the programmer with that task. Programmer productivity is the biggest problem we face today. And then the rest of them give good feedback to the programmers so they can quickly say, oh, here's what you need to do, and have that be expressed as a mapping directive independent of the source code to tune those codes. So let me move on to the third trend, since I'm running short on time here, which is the world is really changing. It used to be we designed our processors, and they went largely into individual machines that sat in front of people, laptops and desktop computers. Those are becoming an endangered species. They're not on the list yet. They're sort of on the list before that, the watch list of species or whatever. But I think they're soon going to be on the actual endangered list, and perhaps even some of them go extinct. Because the really common thread for how people are going to be using machines in the future is that there's a user interface device located near the user, whether it's a mobile device like a phone or a tablet, or whether it's something on the wall or on your desk. It's a UI device. It's not where the computation is happening. And then you have the cloud. Well, why is this? Well, remember that everything is energy limited, right? Today, performance is energy efficiency. And it's really about what experience you can give to a user within a given energy envelope, whether it's the envelope you have in a 1-watt cell phone or in a 5 to 10-watt tablet or in a 150-watt discrete GPU. But if I move some of my computation to the cloud, I can have somebody with a 1-watt handheld device, and I can give them a kilowatt experience because I can be burning a kilowatt up in a machine room and piping most of that information down to them on their handheld device. And of course, they probably don't need that kilowatt all the time, so I have the advantage of being able to share that resource in the cloud with a whole bunch of users with their user interface devices. And by the way, it's much easier to manage if it's in the cloud. The human costs of running a machine are way lower if you take all of the stuff that winds up breaking and you have to call the sysadmin to fix and put it in one place and don't let the users at it. And I already had that on there. What do you know? And it also gives me access to a large amount of data. There are a bunch of things that I'd like to do for that user experience that require petabyte data sets. I'm not going to put that on your handheld device. And I think it's kind of amazing today. One of my first startups was a company called Stack, and we did data compression for PC disks back when PC disks were 10 megabytes. It's amazing to me today that I can have an iPhone that's 32 gigabytes. But I'm not going to have petabyte databases on my iPhone anytime soon. I don't need to. I can access petabyte databases in the cloud. So the future of the world really looks like most of us are actually used to today. We have the average user here, with their hopefully Tegra-enabled smartphone, and they're communicating with the cloud, which has all sorts of Kepler GPUs in it. And a lot of the interesting work is figuring out how to factor computations. So the work that takes most of the energy and has the large data footprint takes place in the cloud, and the part of the computation which requires very high interactivity happens on the handheld device, and the place you cut the two apart has relatively little bandwidth going between them. So we're actually trying to do this for graphics now, looking at how to take the traditional graphics pipelines and split it into different places. We had a paper on something called Cloud Light, where we basically took the lighting calculations. If you want to have really good indirect lighting, you want to do global illumination. That's an expensive calculation, but not one that has to be particularly interactive. The lighting of a scene doesn't change that rapidly. It'll change a little bit as shadows are cast that affect the irradiance matrix. But it's nowhere near a 60 frame per second thing. On the other hand, the actual interactivity of rendering the individual polygons does want to be 60 frames per second. You want to run that on the UI device, run the global illumination calculation in the cloud. The amount of information between the two is actually relatively small. So let me give you some implications here, and then I'll move on. So my view, I'll give you conclusions and then opportunities that come from this, because I figure whenever I address an audience at a university, I should be tossing out to you what I think are the interesting research problems. So large computers today are scientific instruments. They're like the particle accelerators and telescopes of the 19th and 20th centuries as being the primary tools by which people do scientific discovery, or really discovery of any kind, whether it's scientific discovery or discovering things of your business nature or of large piles of data that could be exploited for different reasons. And it really is the same type of machine you need, whether it's to study science or to study data. You may balance it slightly differently in terms of amount of memory versus compute versus communication. Three key trends are really changing the way we build and program machines today. The end of Dennard scaling means that everything is energy limited because we're not getting this back to the baseline after scaling up number of transistors and making them go faster. We no longer get to lower the supply voltage to get back to the same power. Now we wind up being able to put a lot of transistors on a chip, and we're really worried more about the energy that a particular operation takes than how many transistors, because we have more transistors than we can power and run at full speed. That really pushes us to optimize machines for throughput. We can think of throughput as the number of operations per unit energy, then for single thread performance. Because most end applications we want to run are very parallelism, even if many of the codes we have today have single thread critical sections. So everything is going to become parallel simply because that's what our machines are becoming, not just the big supercomputers with billions or 10 billions of threads in one computation, but even the cell phones in a few years will be many thousands of threads. And so we need to learn how to code things this way. Everything is moving to the cloud plus the mobile with sort of self-contained machines going to be becoming an endangered species. So to me, the two really exciting things, this is what a lot of my research direction is focused around, is energy efficiency, because to deliver value in the future, you have to deliver energy efficiency. Performance is performance per watt. And there's a huge gap on the architecture side between what special purpose hardware does and what our programmable machines do. And to me, closing that gap is one of the most interesting questions in architecture. Similarly, there's a very big gap on the circuit side. If you look at critical things like moving a bit across a chip or reading and writing a bit of memory, between what that operation actually costs today in picojoules, what's on my shopping list, and what it should cost. If you go down to sort of fundamentals of what do I need to overcome the actual noise processes that I'm competing with to get information out of this. So to me, energy efficiency through architecture and circuits is the big levers we have to improve the computing world. And actually what people are counting on us to do to replace that 2.8x we used to get from process. Now, all of this is going to be in this context where everything becomes parallel since machines are only getting wider and not any faster. And the huge bottleneck today is actually coding parallel programs. We build these parallel machines. Nobody knows what to do with them because it's too hard for people to code parallelism. That's because they're doing it in that obfuscated way I showed you. They're trying to think of it as threads and locks and forking things, and not in the more data parallel way, which is I have collections of objects that I map functions over. You really want to basically, take your collection of objects, molecules, map a function, forces, do an implicit synchronization, and then move the molecules. It makes the parallel programming very simple, and we really need to make that parallel programming so it's target independent. It's too big an investment to make in writing a code to have it become obsolete when the machine it's running on becomes obsolete, which happens every 2 or 3 years. So here are the opportunities and challenges for all of you bright researchers to go out and deal with. We really need this performance that we've gotten used to. Large parts was a National Academy study that I had the privilege of being on called The Future of Computer Performance Scaling, Game Over or Next Level, sort of viewing it as a video game where you're trying to continue to up the CPU performance. And what it showed is that large fractions of the economy really depend on computing performance, not just what you would expect of the computer hardware and software industry, but things like the entertainment industry is depending on better computing performance to continue to improve the effects that are used in producing all sorts of media. The automotive industry, a lot of the value they add to automobiles these days is by the 50 or so processors that are in a typical car. The aerospace industry adds value to their products, mostly through computing. It was interesting. I met when I was department chair at Stanford with the CEO of Boeing, and I said, what kind of engineers are you most interested in hiring? And I was fully expecting the answer to be aerospace engineers because we need better wings. But his answer was, no, we need software engineers. We need like 2 guys to design all the wings we need for all of time, and they have to train their apprentices. So when they die, there are 2 more guys to design all those wings. But we need thousands of people to write the code that goes on a typical jetliner. And I got similar feedback from the CEO of GM about cars. So it really is a computing-centered world. And if we don't, and everybody in rolling out these new features for whether it's airplanes or cars is counting on headroom. They're counting on the computing performance to continue to scale. If it stops scaling, their cycle for doing another generation slows down commensurately because they don't have the headroom to add those features. And so it's really up to those of us who are in the business of building the hardware to be clever about circuits and architecture to fuel that growth, since we're not getting it from process anymore. The bulk of the computation is going to be on the cloud on throughput cores. And there's interesting questions to ask there about how then do we split certain computations between the cloud and the UI to basically deal with limited communication bandwidth and the fact that bandwidth is expensive, but yet provide a really great user experience for whatever application we're running. The way we typically use it today is we typically send everything up and then send the result back. There have to be better ways of splitting the problem than that. There's interesting opportunities for fixed function logic and novel user interfaces on mobile devices. One of the ways of closing the gap between fixed function logic and programmable logic is use fixed function logic. And we actually do this today. If you look at your cell phone, most of the ops in your cell phone are fixed function, right? There's modems in there doing tens to hundreds of giga-ops. And there's video coders and decoders that are operating at similar levels. Orders of magnitude more performance than the ARM cores in that device, or even than the GPU. And if we can find what the right basic building blocks are, maybe we can basically raise what an instruction set is from being things like add and multiply to being larger building blocks for which we've provisioned fixed function logic. And so parallel software, I left best for last. I personally think is probably the biggest opportunity today because I think it's the if I was to give myself a report card on how we're doing all of these, this is the one that gets the gentleman's D, or maybe not. Maybe it gets the F. Who knows? Because we're just doing a really cruddy job on parallel software today. There's so many opportunities to do a better job in improving the productivity of programmers and automating the task of going from an abstract description of a program to an efficient execution in a way that's target independent. that I think that there's many ripe PhD theses there, and I hope many people will work on them. And I think what tends to sort of get in people's way here is they feel like they need to have a perfect, complete solution out of the box, but nothing ever works that way. If you can just lop off a small part of the problem, that's huge progress. Whether you can sort of come up with a special case. A lot of people now are doing domain-specific languages. They'll lop off a special case of stencil computations and being able to automate the mapping of threads to or tasks to threads and threads to processes, data layout and staging for stencil computations. Huge advantage. All the people who do stencil computations just got 10 times more productive. They wind up with more efficient code. That's 1/10 the lines of code for the same problem than they had before. Domain-specific languages are one way of lopping off part of the problem. Lopping off just part of the optimization problem is one way of lopping off. You don't have to solve the whole problem. Solve just how to pack threads efficiently, or solve just how to do data staging up and down the hierarchy. And later on, people can assemble these and get a complete solution. But big things don't happen, in one step. They take a bunch of little steps to get there. Auto-tuners, it's probably the wrong word because it conjures up notions of things like Atlas or FFTW, but automatic tools for mapping and data layout are a hugely important part of this, as are performance analysis and visualization tools. So I think it's a pretty exciting world to be working in the computer space right now because of these three trends are changing the game and giving us an opportunity to innovate and restore that scaling of performance that people have come to depend on. So thank you very much for your attention. I'd be happy to answer any questions you have.
Thank you very much for the talk. It was brilliant. So I personally conduct exascale research in advanced micro devices, and I work on fast forward project with the Department of Energy. So everything that you've said about supercomputers are very close to my heart. But that being said, HPC codes, in many ways, from the start, they're supposed to be embarrassingly parallel. So when you parallelize them, even for these exascale systems of the future, it's sort of like in many ways it's challenging, but in many ways it's a low-hanging fruit in a way. I'm wondering, you mentioned several times during your talk that the energy cost of moving the data across the chip is high. Do you think it's the same of moving the data not necessarily within the GPU, but also between GPU and CPU? And do you think that if you try to parallelize the software out of the HPC, sometimes the underlying system, the most efficient way to comprise it might be just to use, let's say, latency unit and throughput unit together, so that you, because the problem is sometimes the software is hard to parallelize just because you don't have that much of a parallelism inside.
Okay. Sometimes, you got 2 or 3 questions. I'm going to start taking notes if you ask any more. So the first question is the expense of moving data. So anytime you move data, it's expensive. And the farther you move it, the more expensive it gets. You're moving it locally on chip is still more expensive than doing the arithmetic operation. Millimeter, and you're over the cost of even a floating point operation. 100 microns, and you're over the cost of doing an integer operation. Moving it across chip is an order of magnitude more than that. Going off chip is comparable. It's usually a couple times more than going globally across the chip. And so typically if you go from CPU to GPU, you're going off chip, unless you've got a integrated CPU, GPU, like our Tegra parts or the AMD, I forget what they call them, Fusion parts or whatever. Even there, it's a global communication. It's very expensive. That was step one. Question one, yes, communication is expensive no matter where you're moving it. Question 2 was, HPC applications have lots of parallelism. What about the rest of the world, which is 99.999% of it? So what I found is any computation that runs for long enough that you care about it is running some operation over a large data set. And you can refactor that computation to be mapping a function over that data set. The reason it takes a long time is because you're repeating the same operation on a lot of pieces of data. And the problem is people usually code it in such a way that parallelism is not exposed. And that's why we need to up-level the programming so that we expose all the available parallelism. My observation is even for simple applications that run on laptops and cell phones, that kind of parallelism exists. It definitely exists with the place where you really care about it, which is in the data center. Because if you look at a lot of these data center applications, many of which they are centered on machine learning, they're actually not that different from the HPC applications. They do a lot of linear algebra. They've got very large data sets. They've got huge amounts of parallelism. So I'm not worried about not having enough parallelism to keep the throughput cores busy. That said, to get to sort of your third question, and I remember recall doing better than average here. There are cases when you do want a latency-optimized core. So we're not planning to take them out of the system, but we're trying to move them to a place where they don't consume so much power. Because one of the problems with Titan is that it's got one of those darn AMD cores. I'm sorry, hanging off there, consuming half the power and doing almost no work. It's kind of like your cousin. who comes to your business, right, and kind of hangs around and doesn't do much. You know, so you know, we're trying to sort of factor them so they don't consume quite so much energy and aren't quite so much of a deadbeat load on the rest of the system.
There's a reason why they're there.
Yeah, no, sometimes you have a thread you just need to get done really quickly, and you want that deadbeat cousin around for when that happens. Yeah, up here.
Yeah, so for most of my professional life, like all the cool kids in the hallway were talking about sort of the end of Moore's Law, end of roadmap silicon, and you see that the process nodes are coming slower, right, and the process folks and the device folks are doing insane things to keep pushing that, right? And then, yeah, about, 5 years ago-ish, the cool kids started talking about, Dennard scaling's ended, blah, 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 right? So is this just a temporary sort of blip that we have where we have a few more generations of Moore's Law, and then... Yeah, so what is the end of roadmap, I guess?
So it's a really good question. You know, what is happening with the end of roadmap? So I had the same experience. I started out as a microprocessor designer at Bell Labs, and I was told, there's no way you could possibly scale below 1 micron. Right? In the meantime, at the time I was designing 5-micron chips. It seemed like a long way away. I could spend a lot of time designing microprocessors before we got to 1 micron. And I remember getting the design rules for half-micron technology, and somebody's saying, wait a minute, this wasn't supposed to be possible. What happened to this barrier? Oh, yeah, we moved that. You know, So I'm pretty confident that the Moore's Law part, the more transistors, is going to keep going. I mean, it's going to continue to get more expensive. And because you're not getting as much value out, remember, one of the things that fueled, you know, it's a huge investment in capital equipment and in process development to move to each node. And it gets bigger each generation. And what fueled that was that 2.8x increase in value. You could cost reduce things, so it was worth making the upfront CapEx expenditure to get 2.8x reduction in the per unit cost of what comes out. If the reduction in per unit cost of what's coming out now is only 1.2x, it's less of a motivation to invest in the CapEx. And so it's really an economic question, not a technological question of whether, you know, the equipment manufacturers and the big semiconductor, you know, we're a fabless company, so we don't worry about that part. We sort of track, we fab with 3 different foundries, and we track what those foundries do and get on the best technology. But whether those foundries will be able to continue to afford to develop in the process nodes at the same rate when they're not delivering as much value is a big question that I don't have the answer for. In terms of is Dennard scaling, you know, one of these phantoms like the end of Moore's Law at 1 micron and stuff like that? No, it's real because, you know, sub-threshold current is real, and unless somebody comes up with a device that doesn't have a sub-threshold current that scales exponentially with voltage, you cannot scale the supply voltage down. You'll leak like a sieve, and your chip will just, you know, go poof. You'll let the smoke out.
I mean, that wasn't the question, right? I mean, it's really just how much, basically, with physical device scaling limits, right? Are you just talking about giant chips? I mean, you know, wafer scale integration as, you know, here's your chip, and
yeah. Well, we make pretty giant chips. I mean, the large GPUs are over 500 square millimeters in area. I don't see them getting a whole lot bigger, you know, when we look at new technologies, it's always a question of what value are we getting? Are we able to deliver a more energy-efficient solution, or are we able to deliver a less expensive solution? And both of those are important questions, and you're getting less of that out of new nodes. Yeah. So there's a guy in the back who's waiting.
Yeah. So 2.5 questions. One, your parallel software flow you're proposing was an awful lot like a normal hardware development flow where you're passing the VHDL through some mapping tools. Just sort of an observation. Maybe it's an interesting way to write parallel programs. But 2, you say process doesn't really matter. But on the horizon, we're looking at a lot of new memory types, like phase change memory and such. And so the cost per bit might change dramatically in that environment. And you might need to go to 3D scaling in order to make the process viable. How does that change things? And especially, one thing that GPUs are bad at is core-to-core communication. So this might play into that.
Okay, I'm trying to remember what the first question was.
Just the hardware design process.
Oh, yeah, okay, yeah. So I have to confess, I'm a hardware designer. That's probably just the way I think about the world. But I think it's the right way to do software, too. And I didn't say the process didn't matter. I simply said it matters less. And actually, one place it probably matters more rather than less are things like novel memory technologies, where, you know, things like phase change memory, if the right endurance problems can be solved, really could be a game changer in a lot of ways. Every time we look at 3D stacking, except for DRAM, where we, in fact, use it, it doesn't make sense. Because of thermal reasons. We're not limited by area. We're limited by power, and it's a question of how many watts per square centimeter we can remove, and you know, stacking things on top doesn't help that. It actually makes it worse because we have more watts in the same number of square centimeters. So, yeah, we can go on this side of the room since these guys weren't able to see the slide. Yeah.
Nvidia is sampling supercomputer chip with 192 cores, right? And in the light of what you explained today, I would like to hear from you what kind of programming model you are preparing for that that programming thing. Actually, is that this new paradigm?
So what I'm talking about here is stuff we're doing in the research lab. So for the products we ship today, like the K20 and even our Tegra cores that now have Temporal GPUs on them, the programming model we support, we actually support two versions of programming models. One is based on CUDA, which is basically where you write C code, and then certain of your C code gets tagged to run on the device, which means the GPU as opposed to the host, which means the CPU, and you launch kernels that run on the device. And for certain computations, that's a very efficient way of writing the code. The other programming system we currently support is called OpenACC, which is a directives-based programming system, much like OpenMP, where if you have code written with a lot of loops, you can simply put directives around certain of those loops that will cause those loops to be parallelized and run on the GPU. Yeah.
Is there a metric for energy used to execute an instruction cycle per unit of developer difficulty?
Well, that's a really interesting measure. I've never seen one, but it's something I'd like to look at because it's very often that's what we actually worry about on a design project because we have so many engineer days to put into a design, and we'd really like to know what gives us the most bang for the buck. And we actually try to make that decision informally, but we've never quantified it. Yeah.
Can you comment a bit on value yield costs and things like that? For example, all the things that as you try to make things more energy efficient, those are all the ones that might also be the things that make the die bigger. And hence the cost goes up, and then how do you deal with that?
Yeah, we try not to make the die bigger because hurting our margins is considered a bad thing to do, and I get points off at the end of the year for doing that. So most of the things we're trying to do are sort of neutral to area.
I had a question. So you mentioned architecture and circuits in this context of energy efficiency. What about approximations? Do we need for graphics and so on perfect computation all the time?
Well, that's a great question. So I really should say architecture, circuits, and software. And one of the software areas we're looking at is on reduced precision. It's already the case that we're putting in FP16 because a lot of graphics doesn't need FP32. And if you have the FP16 operations, you wind up significantly reducing both the arithmetic cost, but what's more important is you're only moving 16 bits around instead of 32, and the communication cost goes down as well. By the way, that's one of the things that really hurts you when you move to a 64-bit address space, is all your darn pointers are now 64 bits. We've even been looking at things like compressing pointer structures because the entropy of a typical pointer is very low, and you don't really need 64 bits to represent it. And so it's a real question. The real challenge in doing approximations is programmers get really annoyed at you when they run their code and get the wrong answer. So you need to make sure that you, and it's one of these things where it depends on who the user is, right? If somebody's shooting aliens in StarCraft or whatever, they don't really care if there's one pixel that's wrong on one frame of the screen. In fact, they probably won't even notice it. In fact, it happens sometimes. But if you're doing some weapons calculation, trying to certify whether this bomb is going to go boom when it's supposed to and not when it's not supposed to, you get kind of annoyed if you get the wrong answer. So it's a question of how important the answer is and what approximations you can make without giving somebody an answer that they don't have confidence in. Yeah.
For the parallel software tools, in your own view or in Nvidia's view, whose job is it to make them?
That's a really good question. One of the problems that I think the software industry has constantly been plagued with is competing with free. There's so many kind of free tools out there that the companies that make really good tools have gone out of business because it's hard to make money making really good software tools when you're competing with free. And so I know we need them to happen. I know that Nvidia, we spend an enormous amount of money on developing software tools for GPUs. Both the CUDA and OpenACC, we recently acquired this company called PGI to acquire their compiler technology that we use now for OpenACC. And so we're investing a lot in that, but it's often hard for us to make the case that that's a good business investment for our shareholders because we basically give these tools away or charge very nominal sums for them, and they're very expensive to develop. So it's one of these cases where these tools deliver tremendous value, but it's hard to realize that value as a business proposition. Well, that's over. We have no more questions. Okay.
I have one small question. You mentioned during the talk that when you turn off certain parts of dark silicon, it's not as efficient in terms of power as for example, when you use just, for example, tuning. Can you expand a little bit on this?
This is one of the things where I can't do math up in front of a board. Whenever I teach a class, I have to have the math worked out in advance because your IQ drops by 100 points when you get in front of a board. And for some people, that's a problem. But if you do the calculation, what you'll find is if you have a certain amount of work to do, and suppose you have the choice of, let's say you have a 150 watt GDP limit. You have a certain amount of work to do. And your choice is turn half the chip off and run the other half full bore, right? Or turn all the chip on, throttle it down to where you're at 150 watts and run the same problem. You come out ahead with the second solution. I will leave the math to you as an exercise for the reader.
Any more questions? Not, thank you.